Hello, my name is Jerry Crow, and I'll be talking about the refrigeration cycle because I was a group reporter for it. The objective was to determine the coefficient of performance for the refrigeration cycle, to make the pH diagram with the results we collected from the experiment, and to understand how the different devices work together to create a cold environment by removing heat from the system. The definition of efficiency is calculated by taking what you want, dividing by what you have to put into the system. And in this case, what we want is heat to leave the environment, which is the Q of the condensation. And what we put in is work in the compressor. And the Q for the condenser is the specific heat times the mass flow rate times the change in temperature. And also, it's called a coefficient of performance because it is greater than 1, unlike efficiencies. And for exercise 1, we had to calculate the electric power, the heat we produced, and the coefficient of performance. And the electric power, which is the number that the machine gave us, ended up being 430.9 watts. The produced heat was, that's the equation for it, and the mass flow rate is density times the volume flow rate. Don't confuse that with the heat. So you get Q dot equals 4,180 joules per kilogram Kelvin, which is the specific heat, times 0.0831 kilograms per second, which is mass flow rate, times 4 degrees Celsius, which is the temperature change. And you end up getting a value of 1,389.15 watts. And whenever you divide the heat divided by the work, you get a coefficient of performance of 3.22. And for exercise 2, we needed to create a pH diagram with the measured values, and then we had to compare this with the ideal refrigeration cycle. From steps 1 to 2, you have the compressor, which you put work into the system, and the pressure and temperature is increased. Compared to the ideal compressor, which is from 1 to 2S, and this follows a constant entropy curve. Entropy does not remain constant because you have viscous losses due to friction whenever the liquid is traveling through the piping, and the piston is also losing liquid, so that causes a gain in entropy. And due to the second law of thermodynamics, you have H1 minus H2 is greater than H1 minus H2S, which means you need a greater work input than the ideal case. From steps 2 to 3, you have the compressor, which we assume the pressure remains constant, and you get that you remove heat from the system. From 3 to 4, we assume constant enthalpy, and the pressure and temperature drop. And then from 4 to 1, we have the evaporator, which is where the humid steam is recycled to the superheated steam, and the process starts over again. When you compare the real, what we did, and the ideal case, you see that entropy is not remaining constant from 1 to 2, and for step stages 1 and 3, they ideally land on the vapor dome, but in this case they don't. And we assume that 2 to 3 and 3 to 4 were ideal, but then from 4 to 1 in the evaporation region, pressure drops because of the resistance in the evaporator. And the thermostatic expansion valve is where the expansion happens. It's located between the outlet of the condenser and the evaporator. This causes a pressure drop. There's a sensing meter at the entrance of the compressor, which senses the temperature at this point. And it changes the amount of refrigerant that's passed through the valve. So say if the temperature is too hot at the entrance to the compressor, more refrigerant is pumped through, and vice versa for if the temperature was too cold. Some uncertainties: the resolution of the temperatures and pressures were 0.1 degrees Celsius and 0.1 bar, so we couldn't be more as accurate as that. And whenever you interpolate, you're only approximating the enthalpy, so that leaves an error too. And the slight pressure drop that happened in the condenser was neglected because it was so low, but this will cause an error. And also we assumed enthalpy to remain constant in the expansion valve, even though this is not the case.